Hi, welcome to this session. In this session, I'm going to explain another problem about magnetic fields with moving charges, well, moving particles. And in this case, we have, I don't know if you can see this, but that's a way to find, well, for me to see where I can write, because at that point, the light that's over there, it's well, that's not the point. We have this problem where we have a wire, coaxial wire, that it's made of copper, and around it we have a shell also made of copper, and well, the wire has a current I that's pointing towards you, and the shell has a current I that is pointing outside of you. So, well, they're asking about the magnetic field and how does the magnetic field um, present itself inside the wire, between the wire and the shell, inside the shell and outside the shell. And well, they're asking about the magnetic field and also about the current because, as we all remember, um, the magnetic field that is created will be, well, it depends on an existing current. So if at some point we don't have any current, then we will have no magnetic field. And so we will start. I'm gonna just try to so that's what I was talking about. Here we have a radius A. Here we have a radius, oh wait, the shell. I'm terrible at drawing circles, like terrible. But this is B, and that'll be C. So we got this small. This would be the radius A. Then, well, from the center to just the beginning of the shell, we have the radius B. And from the center to the end of the shell, we have the radius C. And, well, once I said that, I'm gonna just A, B, C. I'm just gonna write it there so you don't remember. A is the smallest, C is the biggest. And, well, as if you saw my last video, we know that if we enclosed a circuit, we can deduce some things about the magnetic field and the current, and so that's what we're gonna do here. We're gonna use this equation, ds equals mu naught I enclosed. And the first thing that we can analyze is that if we go outside the shell, we would have an enclosed current. This enclosed current I minus an enclosed current minus I. So if our current enclosed is equal to 0, then our field is directly equal to 0. So outside C, outside that shell, we will have no current. And if we locate ourselves inside A, like where our radius is smaller to A, then we can know what's our magnetic field inside the wire. So the first thing is inside A. Inside A, we got that the current enclosed is equal to the that's integral of the current density times the differential of area. We know that the current density it's equal to what? We know that J1 it's equal to the current over pi times A squared. A squared would be the radius, like that's the you remember this, right? Current density is equal to I over area. Area, that's, so what are we using right now? We're grabbing what would be the current density at A, and we're locating that inside of an integral. So our next differential of area will be our enclosed surface. So we'll say, okay, if we had this big cake with this current density and we locate ourselves at the radius r and we grab a piece of that cake, then we would have a piece of cake depending on the current density that we will respect at that point. So I know that I may be hungry. So we got using that equation, we also know that as we have that's our surface, and that's R, and that's B, and that'll be ds. So we will have B times 2 pi the radius. Yeah, that's the radius. Yeah. B1, that's our first enclosed surface. That'll be equal to mu naught times, as the current density it's always constant, then we can, and it's a constant, it doesn't need to be inside the integral, so we can take it out, and now we would have I pi a squared, and that'll be multiplying the area, differential of area of this surface. And if you remember, when you have only a differential of area from 0 to that area, then you can write that as only the area, and that's pi r squared. And if we solve for B1, then we would have mu naught times I times 2 pi r over a squared. And that's correct. And well, if we now try to find, you can screenshot that, and we're gonna locate ourselves now between the wire and the shell. So we'll try to find it. That's between A and b. Well, between A and B, it's pretty simple because our right side would be mu naught I. Why? Because the charge that you're enclosing with your cake is like all of the charge, and the only thing that changes is the radius, but the equation doesn't changes at all because you have the b2 times 2 pi r. Just we need to take in consideration that this r is between the radius a and b, and so we have b2 equals mu naught I over 2 pi r. And yeah, that's the equation for B. And at C, at some point of the radius C, well, of the shell, so that's between B and C. So at some point of the shell, we have well, in the left side of those, we keep with the same context. We have b times 2 pi r, considering that r is between b and c. And now what it will changes is the current density. So the current density will change as if we have mu naught multiplying 1 plus, I'm going to erase that, 1 plus the, well, this 1 is because, no, that's not a 1, that's a 1? No, that's not a 1. That's I times the current density of, well, yeah, times I of the shell. And I of the shell is basically the integral times dA. You remember that from this first step of our problem. And what we basically expect is to have a minus sign over there, so that as the radius increases in the shell, it will start taking I, because our I in this case is negative, so that will be happening because J2 it's equal to minus I over the differential of surface radius, and so we will have P times C squared minus B squared. So just like that. So we're taking only this part, and so we will have that, and we will mu naught times I minus I over 2, not over pi C squared minus B squared. That will multiplying the differential of area, and in this case, this differential of area is not from 0 to something. It's, well, I have it over here, so I'm just going to write it. It's pi r squared, yeah, minus pi b squared. And when we solve that, we obtain mu naught over, well, mu naught times probably I, yeah, over 2 pi r times, well, that would be B3 times I minus r squared minus b squared over c squared minus b squared. And the last part of the problem is asking us to graph our distribution of magnetic field. So we will have something like that, and this would be point A. Well, that would be point A, and that would be mu naught I over 2 pi area. And then we'll have something like here, mu naught I over 2 pi b. So as you remember, at C, that would be B and C. At C we have zero magnetic field. At B we have less magnetic field than we had in A, because at that point they will be going away from the center of the magnetic field. And at A we have the just a direct increase of current of magnetic field. And well, that'll be all. And thank you.